ready to rock, sir? All right, here we go. Rock and roll.
Hi, I'm Theresa-Marie Rhyne, and I'm here today to talk to you about color basics for creating visualizations. This is part of the IEEE VIS 2020 Conference Week. So in this tutorial, we're going to cover 4 major areas. We're going to talk about a review of color models. We're going to do a little bit of color theory and color vision. Then we'll look at color gamut systems and displays.
I've got my video down low. Will said
That's
to put it down low. I've got it down low.
Where we'll have question and answers afterwards. Our second video is
that just came across here on the
tools,
YouTube.
research, and case studies in color. Then we'll have a little question and answer after that one. So let's begin looking at color models. The first color model is the red, green, and blue color model that is used in displays and mobile devices. It combines red, green, and blue lights to create a final white color in a projector type system. The next one is used in printing, and that's cyan, magenta, and yellow. Basically, it's called a subtractive color model because the final result is black in printing, and the K actually stands for key black. The final color model is red, yellow, and blue, and this is how we mix paints together. It's also considered a subtractive color model. The final product is more closer to a brownish color than an actual black color, but this is the color model most of us begin with using when we started studying color in kindergarten. Now there is an inverse relationship between red, green, and blue, and cyan, magenta, and yellow. That relationship is such that red is the complement of cyan, green is the complement of magenta, blue is the complement of yellow, white is the complement of black. And if we were in a perfect world, we could transparently move between RGB and CMYK. Most of us know that we're not in a perfect world, and that when we create a visualization on our display systems, it looks a little faded or duller when we print it in CMYK. So this is what a comparison is between moving between a display process and a print process. Now here is a particular visualization of the complementary nature of the two color models, and as you'll see, when we see it in RGB space, it's a little more vivid than we see it in CMYK space. Isaac Newton created something called the color circle. This is actually a key visualization paradigm for understanding how color behaves. Basically, he had a series of prism experiments where he was taking light and sending them through the prisms to create and isolate the various different colors on the color spectrum. Then he decided that it would be really neat to take that color spectrum and put it into a circle. So he put red, orange, yellow, green, blue, what he called indigo, and violet into the first color circle. Now, if you look at it, you'll notice there's a color missing. And I'm going to describe that a little bit later in a couple of seconds. As Newton's color circle evolved, it became the color wheel over time. And here I show some historical displays of the color wheel. So this is how it evolved over centuries since Newton developed it in 1666. Now in 1810, Goethe came along and he put a color called magenta on the color wheel that has stayed there ever since. He came up with some other color theories that expanded Newton's initial concepts. Rhyne, who was a colleague of Goethe's, also was the first one to think about, or publish, we'll say, a 3D sphere and come up with the idea of a color sphere concept. Now, we're going to talk about later in this course how that concept didn't quite work out as a visualization paradigm. There is also a very critical player in all of the understanding of color theory, and that's Chevreul. He was a chemist. He was in Paris, and he was hired to understand tapestry phenomena that was occurring. And this phenomenon was the following. You could have threads that looked very vivid, strung individually, but when they were combined, they began to look faded and they began to interact with each other. People thought that somehow there was some kind of fading in the chemistry, or somehow the colors and threads interacted with each other and causing some kind of mixture. Chevreul was to show that it's actually an optical phenomenon called simultaneous contrast. Our eyes were producing the contrast. So how you combine colors together makes a difference. And here I show you the example of an orange square background with a cyan on top, and also a cyan background with an orange square on top, and how we see those colors differently. In terms of our world of visualization, what that means is you don't want to mix them together directly on top of each other. So what I show you here is a tree map, and you'll see that these two colors on the color wheel are considered complementary. And what we want to do is when we build a tree map, we want to keep them slightly apart from each other to display the information if we're going to use a complementary color scheme. So that's what I'm showing with regards to this example. As we know, the tree map concept was originally developed by Ben Schneiderman and his team, and I'm showing you this example created in Tableau. I'm also showing you an interesting relationship. It turns out the Mondrian types of displays, Mondrian was an artist, and he is the one that you can see him in his concept on the left, where he created a mosaic type effect. It actually is a good display test up against a tree map. And I show you a tool called Palladium Color Scheme Designer that does that, just for fun. So now we're still talking color history here. And we're going to talk about the first real presentation of RGB color theory. As we look back, let's remember that James Clerk Maxwell demonstrated this in 1861. And in his world, painters described color as red, yellow, and blue. And they had all kinds of color harmonies that existed. Maxwell would get up and lecture at the British Society, the Royal Institution, and he would, for the first time, produce the first red, green, and blue color photograph. He took various filters and he showed red, green, and blue combined together to create an image of the color. Now, this was breathtaking. This was revolutionary at the moment that he did that. So imagine, it's pretty exciting in visualization. So it turns out that Maxwell's writings and other types of, and Chevreul's writings were synthesized by a guy named Ogden Rood, and he wrote a book called Modern Chromatics, and he managed to get it down very simply. Rood was an artist, and he managed to get these concepts down where he summarized additive and subtractive color models. He concisely presented what complementary colors are, and I'll talk about that later. He diagrammed the color wheel. He defined hue, luminosity, purity. And after he studied these color theory concepts, artists took them and applied them to their paintings. They basically worked it out through artwork. This resulted in things like pointillism, divisionism, art movements, and perhaps the one we most know today is Georges Seurat, where he showed how you put a series of points together and the eye can complete the colors. Now, Seurat developed this in 1886, and it relies on the eye and the mind of the viewer to compose the color dots into a broader range of tones. This basic concept, however, has been used very heavily in our world today. There is such a thing called point graphics, point-based computer graphics that's used, and there may be some presentations here that talk about it at IEEE VIS. The CMYK printing process uses a color situation where printers are dot-based. If you look very careful at a CMYK printout, you'll see its little dots coming close together to form the colors. Televisions, computer monitors, phone displays use the same thing. basically what's happened is the dots come close together. So I talked about red, green, and blue lights. So if we combine red and green together, it doesn't seem logical, but this is true, red and green together, we're going to get yellow. And if you look carefully at a display system very often, that is an illusion that our eye accepts and makes. Band-Aid dots was a printing process, is still a printing process used in camera cartoons, and it basically uses color dots widely spaced or narrowly spaced to create its particular optical illusions. Ben-Day was the illustrator that came up with the concept, and the artist Roy Lichtenstein probably enlarged and exaggerated this method in some modern art today. Okay, now I want to talk about a tool that's freely available for looking at color proportions of an image. So let's analyze some of these paintings because we want to learn about color ourselves. And this is how I have learned about color. I go to museums, and I even, in the world around me, I use my tools to capture a color image and understand what's going on. This one, I'm looking at a Monet painting at the North Carolina Museum of Art because I live in Durham, North Carolina. It's not too far from me. And basically, I've run this through a color proportions tool to see that what we pretty much obviously can tell, and that is that there's an orange dot which represents the sunset, and that stands out with regards to the Impressionist painting. And Monet was a master at this. Now I'm using another tool called Adobe Capture. It's a free app that you can put on your phone device. And basically, I have captured this particular painting. And what I'm doing here is I am looking at how Monet created this image in terms of trying to understand the color science of it. If you look very carefully, you can see all of these colors are about the same value, but with a little slight difference. So he's got very light colors. Now, Monet was a plein air painter, so it looks like what he did is he had a lot of white in the center of his palette, and then what he did is he varied it slightly to create his imagery and his process. One of the key areas of teaching that influenced color theory a lot in its history is called the Bauhaus. It's a school of design that actually celebrated its first 100-year anniversary just recently. So it began in 1919, and that's about 100 years ago. And many of the instructors developed their teachings after that time. And you have some of the rock stars of color right here. We have Paul Klee, Kandinsky, Eaton, and Albers. And at one point in time, they were all together, and they were like faculty at the Bauhaus, and they were each required to rotate teaching something called the Fundamentals course, which included color theory. In the process of having to do that, it was like the fundamental course that every student taught. They had to work out a lot of their own color theory examples and various paintings and things. Over time, Eaton would go on and publish something called The Art of Color, the subjective experience and objective rationale of color, that would become still a textbook today. Albers would go on and publish The Interaction of Color, that is even an app today that we can look at, and I'll highlight that further. So let's look at Albers a little bit further now. Albers, German born, he immigrated to the United States due primarily to World War II. So he basically, when he got to the United States, he taught at Black Mountain College and eventually Yale University. For years, 25 years, he did color studies, homage to the square, where he embedded various squares of different colors inside of each other. And many of you have probably seen this artwork that is pretty famous now. In 1963, he kind of synthesized a lot of his concepts about color in a book called The Interaction of Color, where he detailed his color theories. It was originally a large format coffee table book, but it was so popular that it became a book smaller in size that people could port around. It was designed for teaching these concepts. He ended up inspiring many students that took from him. Kenneth Nolan was one of them. And Kenneth Nolan basically studied targets or circles rather than his teachers studying squares. And you'll see some of these particular color studies here. Now, you will see that my mother is standing in front of these paintings. There is a particular reason for that. The reason is these artists are relatively, they haven't been passed into heaven that long of a period of time. So I didn't want to get sued for doing these color courses. So I figured I could always say that these particular examples are my mother, and she happens to be standing in front of beautiful artwork. I've never been challenged on the copyright of either one of these images, but I just wanted to be sure. Okay, so in terms of the interaction of color by Joseph Albers, as we get into this, it turns out that we're not the only ones that are fascinated by Albers' work. Maybe you're not fascinated, but I am. You will find out that he wrote this incredible book, and folks decided, hey, let's modernize this idea, and let's make an app. Let's make an app for the iPad so that people can learn how to do these particular color studies on a mobile device. Now, you're going to look at this, and you're going to see a weaving concept here. There's an inside deal about Albers. Albers was married to a woman named Annie Albers, also who was at the Bauhaus, and she is a pioneer, or was a pioneer, in textiles and weaving. And you can see Albers, Joseph, the husband, was influenced by the work of the wife. And he's doing some color studies and basically weaving here. Goes all the way back to Chevreul, isn't it? Amazing how these are all related to each other. Here's another color study. And then here's one that both of these, I'm showing you the image you're seeing on the right is the image that I did in using the Albers app for the iPad. Now, I have since used the Albers app a lot, and if you follow me, you'll know I have a blog and I publish a lot in terms of color studies, a color study every day. I have since used the Albers app concept for visualization, and here I'm showing you an example of taking the Albers app and developing a bubble chart visualization. I'll also cover another example later in this course, probably in the second part of the video. Okay, so now we're going to talk about some color vision principles. Let's think about the trichromatic theory of color vision. I'm going to cover that. Then I'm going to cover the opponent processing of visual perception. You want to know about that because many of you probably use the CIE Lab color model, and it's based on opponent color processing. The coexistence, therefore, of trichromatic and opponent theories. And finally, color deficiencies. So trichromatic theory of color vision. So we've got red, green, and blue. Or in my diagram, I'm showing you blue, green, and red. Either way is okay. In 1802, Thomas Young is the one who first postulated that probably in our eyes we had 3 photoreceptors, cone cells, that were continuing to control our color and our color vision. It would not be until 1850 that Helmholtz verified that, von Helmholtz. And he classified the cone receptors, and he showed, yep, what we got is we got long preferring, which they called red, medium preferring called green, short preferring called blue. Now, our eyes are not like a cell phone. We are not a projector projects out of red, green, and blue light. Basically, in terms of our cones, we're seeing over a range. So I have a diagram here that shows you the blue, green, and red range of our projection. So in terms of green, for example, it's over a range that actually expands from about the violet color that Newton talked about all the way into the red color. But long preferring, medium, and short is actually now called red, green, and blue in terms of defining color vision. Now it turns out that color vision is a little more complicated than this trichromatic process. And this guy named Ewald Hering began to think about this a lot. And he wrote a paper on the theory of the sensibility of light in Vienna, because that's where he was from. And he basically said, hey, in terms of lights, we go out into the world, we don't see mixtures of red and green lights. We also don't see mixtures of blue and yellow lights. Now, this is going to be a little hard for us because we basically remember the red, yellow, blue color model, and we start saying to myself, hey, I can mix red and green together and create some paints. It doesn't look so great, but I can do that. And if I definitely know, hey, I know that if I mix blue and yellow together, I'm going to get green. That's in the RYB color model. What I'm talking about is the red, green, and blue color model of lights. So he developed a color theory called opponent color theory. It said red versus green, blue versus yellow, black versus white into the world. These are opponent colors that are not perceived together. And he came up with a 4-color system of red, green, yellow, and blue. Now, when Herring read this and saw this, he said, hey, this Herring guy's crazy. He doesn't have any touch on reality whatsoever. Don't listen to the guy. Well, years later, it would be shown maybe Herring had a little bit right. And in the 1950s, Eastman Kodak began to see the red, green, blue trichromatic color model wasn't completely defining what was going on in vision. So they had these 2 scientists, Hurwitz and Jameson. They looked at qualitative data, and they kind of, for lack of a better term, proved that Herring's opponent color theory was kind of valid. They basically came up with a Q cancellation method where they showed red and green lights mixed together produce yellow, not reddish green. So Herring got it. Blue and yellow lights mixed together produces white, not yellowish blue. Now, if you think about it, that makes sense, because I told you that in the RGB color model, red, green, and blue, when they come together, we're going to get white. So if red and green produce yellow, then yellow and blue, when they come together, that's going to produce white. So red and green cancel each other out as yellow and blue cancel each other out. And basically, in their experiments, they took a bluish-green light, and they showed it's possible to mix a yellow light with a bluish-green light, cancel it out, and get only green. And this was revolutionary. Today, we accept it, but it was revolutionary at the time. It wasn't that long ago. So the important thing to now think about is color deficiencies, because now I've just told you that we have sort of red, green, and blue cones firing in our eyes all the time. And it turns out that if you have a slight color deficiency, and we're going to talk about this a lot, you could have something like protanopia, which would mean that your red retinal photoreceptors are kind of absent or are not firing completely right. And that would mean that you're going to have some trouble telling the difference between red and green. The same thing's true if you have deuteranopia. This gets to be really important in visualization. If you put some visualizations up there that are red and green, someone who has one of these deficiencies would be able to tell you what's going on. Tritanopia is a more rare particular color vision situation, and that is having the blue cone not firing correctly, and that makes a little trouble to see the difference between green and yellow. With you confuse blue with green and yellow with violet. I show you these diagrams. Now, I wanted to run through, I'm going to talk about this a lot as we get in looking at some case study examples, but I wanted to run through our tree map example I talked about earlier and show you that if you have a deficiency in what you're seeing as the visualization is a little bit different, and how you see it is different. And this is something that you want to check with regards to doing your visualizations. Now, some other work we're going to talk about is non-uniform distances between hues and rainbow color maps. This is particularly popular in our visualization culture. We have talked about the use of the rainbow color map because for a long time the rainbow color map was the default color map in visualization tools. And with regards to trying to understand what's going on here, it's often said that it's non-uniform. Basically, the spaces between the red and the orange range is different between the spaces between the yellow and the green range. So visually, it's very difficult if you show a rainbow color map and then you put something like a scale of 1 through 10 across there. Now, there have been a lot of people that have written on this, And there's been a lot of work done. And basically, in Matplotlib, they changed the rainbow color map to be the Veritas default color map, which is going to go from a bluish, purplish indigo color all the way to a yellow color as the range for the particular colors. Now you can read about how they came up with their changing their color maps. I'm not going to spend a lot of time going into it, so I'm going to tell you that it's important and that there are a lot of people in our visualization community, many who may be involved with the IEEE VIS conference, that have written on it. A lot of this work has been presented at the conference. The first person group was Rygowitz and Trinish at IBM. Borland and Taylor went through and analyzed how often the rainbow color map was still being used as of 2007. Then you're going to see some, Kenneth Moreland has done some work on 2016, looking at why do we continue to do this. And Colin Ware and his team has also done some other sequences, so if you want to read this. The important thing to remember about color is it's very imperfect with regards to our ability to perceive it. It's very easy to have color change depending on what kind of background it's up against. It's a very slippery slope. In human brains, it's been shown we can't differentiate between a yellow light and a red and green light shown simultaneously. And projectors know this, so they shine red and green together, and our brain says, oh yeah, I got it, that's yellow. That's yellow. It also turns out that we have a wider range of red and green hues than blue and green hues when we see this. Munsell discovered it, and that's why the spherical color model doesn't exist in terms of our world of human perception. You can do it, but it's not accurate in terms of human perception. So let's define a few color gamut spaces in terms of discussing this further and see how Munsell discovered this. I'm going to talk about the Munsell color system. I'm going to talk about how a color model and color gamut come together to make a color space. We'll talk about perceptual uniformity and how today we have CIE Lab and Love. I'm going to talk about saturation and value, hue, saturation, and value, which is another color model. Web hex triplets. And then I'm going to talk about Pantone, which is a nice thing to know if you're going to deal with other designers. And yeah, there are apps for all of this on your phone or on your desktop. I'll go through them. So let's look at the Munsell color system. Munsell came along, it was in the late 1800s, and he basically wanted to find a color system, a 3D color space in the 1890s. And he basically was going for the 3D sphere concept. He did various perceptual color experiments. To get it down, he wanted to be in numbers of 10. He decided red, yellow, green, blue, and purple. He eliminated orange from his particular color system. For centuries, it had been a 6-color system. He eliminated orange. That's sad for me because I love the color orange. But then he created 10 steps, divided into 10 sub-steps to come up with his 100 values, hue values, and integer system. He had a value system where black was at the bottom, and in 10 steps you got to white. And then he had chroma measured from the outwards, and he thought it was going to be from 0 to 10 in this beautiful system. And he thought the center of the system would be 5. And everything was going to work out honky-dory, just beautiful. And then the hue was the actual color we were going to get. By the way, this concept that Munsell developed was about 100 years old. I was at the Munsell 2018 conference that celebrated his work. So here Munsell is out there making his experiments. And here is the perfect 5. So this is the color circle, the color wheel in Munsell notation. And it's looking really good, isn't it? It's looking really great. But then his perception experiments came back, and he found out, guess what? In terms of blue and green, our spectrum goes out to about 6, but in terms of a red hue, we can go out to 18. So we're going to get a pear shape when we look at this particular diagram of what our color looks like, and I showed that to you earlier. We're not going to get a spherical ball, we're going to get a pear shape. So in terms of trying, if you want to look at it as a digital color atlas, Munsell made this an atlas. He decided not to mathematically connect the dots between the various different colors. What he did was made what is called a Munsell tree, where everything hung out together. He did not create a spherical or any kind of shape, but rather he created an atlas of color. And this is an example. And here you can find this online if you want to look at the Munsell example here. Now, as many of us who love to do 3D spheres and spaces came along, we tried to create shapes between, but mathematically, in terms of the Munsell space, he did not show in a mathematical correlation between his tree of colors. Okay, now let's look at color gamut. The color gamut for an sRGB device, which is the default system on your mobile phone. This is the triangle I'm showing you inside this horseshoe here. Graved out, it represents the entire color range is the horseshoe that's available. Now, in terms of trying to understand color models, the RGB color model combined with a color gamut will give you a color space. And I'm going to talk about a couple of color spaces here. Let's look at sRGB is the inside triangle. That is the default. Microsoft and HP kind of developed this and sort of around the late 1990s. They came up with a model that is basically the default on your mobile device or on your desktop computer. That's what systems default to in terms of color. Now, inside of that is a little, if you look at the system of CMYK, it's called matte paper in this diagram, you can see it's outside that range, and that's why we get some of the haziness and the differences between moving between the two models. Then Adobe said, look, in our Photoshop and in our tools, we're going to have an Adobe RGB triangle that encompasses both CMYK matte paper and our sRGB together, so that if you select a color, the chances are that it's going to work with regards to our Adobe RGB system. Now we have photographers that are looking at digital media. This is from Kodak, and they go ProPhoto RGB. Now, if you look at that triangle, it's possible to shoot some colors that are registered on your camera, but that you can't see them because it's outside the horseshoe range. So those are particular color gamut spaces that are most well known. Now, right now, I'm going to talk about the CIE XYZ color space, which was developed in the 1930s. And basically, perceptual studies were conducted by Wright and Guild in the 1920s, and then they built this 1931 XYZ color space. And basically, it's an effort to, remember, we're 1930s, so they're not used to having 3D displays like on a cell phone. So they try to show all the mathematics together with relationships and mathematical combinations of the 3D planes in a horseshoe relationship. And that's what this is right here. Now, in order to get these values, they had to run these experiments. And Munsell was doing the same thing of color matching by observers. So what's going on here is that you stare at a light, and if your eyeballs are calibrated properly, if you don't have a color deficiency, you are asked to match that test lamp that comes out as yellow, and you're asked to turn some knobs and combine them together and produce that same yellow with regards to matching the test color. Now, the problem can be you might add a little and subtract a little, and there are all kinds of formulas for how you come up with it, but the color matching functions are then developed to create XYZ color space. Believe it or not, they did the same thing for the other color spaces I'm going to cover. So color perception, we're not perfect, but that's what all the data is based on. So if we want to understand a chromaticity diagram, remember what I'm saying is we're trying to get into a 2D plane, X, Y, and Z, 3 dimensions. So all visible colors for the average human eyes are contained in this horseshoe diagram. The edge of the diagram is called the spectral locus. the least saturated colors are at the center of the diagram. There's always a white point when you look at these diagrams. Any two colors along a given line between the 2 points are made by mix of the colors at the endpoints. So if we're looking at the line of purples down there, if we combine, we can get magenta when we combine red and blue together. That's basically what's going on with regards to that. The line of purples is a good way to examine the combination. Now, as time went on, so we're talking in the 1930s, as time went on, people began to say, hey, I'm not sure that this is perceptually correct, this XYZ stuff, because I think it's heavy on the green. I think the distance between 2 points in green is a shorter distance than, say, the distance between a yellow and a blue. And this is actually shown to be the case. And what they did was, by the 1970s, they were getting new data, and they came up with a new space, LUB, CIE Lab Color Space. And this was designed for display systems, putting it out there. And you're going to see that it really changes a lot between, it's not as heavy on the greens. Now, CIE Lab also came along based on opponent color theory. Technically, it's not a diagram like the horseshoe diagrams that I showed with X, Y, Z, and LUB. It's an opponent color theory associated with equations and things. But today, Lab has become very popular, especially in our visualization community, as a color model for testing. Okay, it also turns out there is another space, cylindrical coordinate space, called LCH, for trying to understand. It's CIE Lab. It's similar to CIE Lab, but it's developed for understanding displays. And again, we're getting back into a display system. But a lot of people like this because it's considered perceptually to be very closest to how our eyes perceive color. So this, for some of you who have large displays, you might like this particular color system, cylindrical coordinates. So here we transition between color diagrams. So we go X, Y, Z, and we fall in love, and we have CIE LUV diagrams. Now, there became, as we get into the 1990s, there became a need to understand color appearance models. In other words, how to match your display with your resulting hard copy production. And the same group of people in the CIE world began to develop a lot of theories and a lot of realities, shall we say, and in terms of color appearance models. And you can read this, CIE CAM, and there's a lot of discussion on that, and I give you some references here that you can look at. Probably one of the best textbooks is Fairchild's Color Appearance Models by John Wiley and Sons. It's a 2013. There's a new proposed color model. If you're kind of into it, it's called CAM 16, a course from 2016. It's kind of evolving. It may become something that's used heavily, but this is kind of where you can find information. Color Spaces is a good tool for converting between the two. Now, why do you care? You might say, you've been talking about all this stuff. What do I care about this? Well, you care if you're going to look at your next mobile phone. You care because Apple uses a wide gamut color space. This particular color space is what it made decisions on with regards to streaming media. It's a wider color gamut than sRGB, but it's different from Adobe RGB that I talked with you about. And it results in some challenges in that which you use in photography and in creating digital media, even like film, is a little bit different than what their standard, which is DCI-P3. Now, DCI-P3 is a standard that people who make projectors used. They never intended to be a standard for people like you and I who do visualization for what we're going to use in our display. But Apple said, no, we're going for it. We're going to design our streaming world in the DCI-P3 arena. So there's been a lot of discussions about this. But I'm going to show you that's the standard for digital camera systems, digital cinema systems. And it's designed, again, let me say, for projectors. It's not intended for consumers to create content. So what's going on here? What's going on is a lot of digital content is created in an Adobe RGB color space. Then they're emulating the DCI-P3 standard. So this is what the streaming media, this is what's going on when you have cinema, digital media produced. Now you start to care because say you have your iPhone and you want to understand your color management system. The first thing is if you have an iPhone 11, you have what is called a liquid crystal display system. Whereas if you have an iPhone 11 Pro, you have an organic light emitting diode system. You have richer color with the Pro than you do with the regular. Now, in terms of their display system, they are using the DCI-P3 precision display technology in terms of their iPhone 11 Pro to get very accurate color matching. It's going to be heavy on the red side. It tends to be a little more reddish, whereas if they had used something that was based around Adobe RGB, it'll be a little more greenish. So, if we look at Samsung, which is another competitive mobile phone device, it basically had to take up the DCI situation because Apple went after it. And they provide a natural mode of DCI P3, and they're 100% accurate with regards to TV content. They also provide another mode called sRGB. So they have a vivid mode and a natural mode. In terms of now, the interesting thing about Samsung is most people go to defaults. On iPhone, you must accept what they put as your content. For Samsung, you can change your display systems if you want to, if you want to read the manual. Okay, if we compare every year, say the Galaxy phone will be a little better than the iPhone. Now I'm going to show you the Galaxy S20 and the iPhone 11 Pro. There's a chance, since this video is going to probably be shown in October, there's a chance that iPhone products the iPhone 11 will be old and there'll be another iPhone product released by Apple. So these diagrams will be out of date. But every year there's a calibration between the two. Now, to this point, it has not been successful expanding the entire horseshoe, but you'll see these triangles have now expanded to the edges of the Gamut system. But there has not been an effort to expand the triangle outwards to try to get the whole. So far, nobody's gotten the whole gamut, horseshoe gamut. But this is a very competitive in terms of supporting streaming media in your mobile devices. Now, how do we calculate color displays? How do you know what's going on? In terms of color display systems, I'm showing you something called ColorMonkey from X-Rite, and you put it on your device and you measure what kind of colors you're seeing. And every single display system is a little bit different. Now I want to talk about some cylindrical coordinate representations of the RGB color model. This was extremely important in the 1970s and is still important today. So I'm talking about hue, saturation, and value, and hue, saturation, and lightness. They're cylindrical coordinate representations of RGB. And they were very important in terms of early computer graphics display systems because the attempt was to make RGB more intuitive. Now, what do I mean by that? What I mean by that is the following. If you were on a particular display system and you had a yellow, what I show on your left, and you decide you wanted to make it a little duller, the image I show on the right, it turns out what you did get is negative 41R, negative 31G, plus 21B. That wasn't exactly intuitive for in terms of building colors and designing colors on your display systems. So what happened was a guy named Alvy Ray Smith he went back to something Ogden and Rood talked about called hue, saturation, and brightness. And Alvy Ray Smith, who actually was a founder of Pixar, came up with hue, saturation, value. So he's showing the hue, the saturation, and the value, and expressing color in those terms. And it's about sort of a cone shaped device. At the same time, at the same conference even, SIGGRAPH, 1978, Jablov and Greenberg came up with something called hue, saturation, and lightness, which is a double cone system for trying to resolve this issue of creating color in a display, using color pickers in a display environment. Now, the reason you care about hue, saturation, and lightness is if you ever are designing anything like on a web pages and those types of things, it turns out the web consortium supported hue, saturation, and lightness. So if you knew the HSL values of your particular visualization, you could enter those particular values into your code rather than trying to figure out the web hex codes, and it would display an HSL. Sometimes that can come in handy for having a richer color capability. So here I'm showing you a comparison between the two systems. HSV was adopted a lot in color pickers on terms of computer displays. HSL became a lot with regards to the web world. So now we're talking about web color hex triplets. So as we look at that particular situation, again, we go back to the red, green, and blue, and we have bytes. A red value is byte 1, byte 2 is a green value, byte 3 is a blue value. And basically, you come up with for any of the 3 color values is less than 10 for 16 decibel. It must be represented with a 0 so that the triplet always has 6 digits. And so I'm sure you've seen web hex triplets before in terms of defining colors, and I show you some examples here. Now I want to cover Pantone. Pantone's a color matching system. It's used to standardize colors, and basically it has no scientific merit based on what we've covered so far. Yeah, you're going to say, wow. But what it does have merit is, and I'm going to talk about this, let's go back to the time of the Beatles, and they're recording an album called Yellow Submarine. Remember, we all live in a yellow submarine. Now, that's pretty bright yellow. It turns out that that particular yellow, they did that in the United Kingdom. They call up Hollywood because Hollywood's going to press that record in Los Angeles, the recording industry. And they describe this yellow. Guess what? They didn't match the yellows automatically. It didn't work out so good. The yellows were a little different. And it turns out the Pantone color matching system was developed so that if I have a particular yellow, I can say what my PMS, Pantone matching system value of that yellow is. I'm in London. I tell the guy with my British accent what that PMS value is. And today I probably do it with a text message. And the guy in Los Angeles gets that message. It could be a woman too. Either one. They get that PMS value and they can match that in terms of creating a color poster for me. So my PMS values work. That's what the Pantone system is about. It also turns out that Pantone's color matching system, and I'm going to cover that later in the second part, is a little bit beyond CMYK. The colors are a little more richer. So Pantone also ended up providing CMYK values. So here's what you can do. You've got this nice little visualization. This is something I did a number of years ago with my colleagues at the University of Utah. And you want to print it maybe for a poster. You can run this through the Pantone Connect mobile app, and you can determine the basic Pantone color values, and you can specify those color values for printing. And I'm going to run an example again about it later. Now I want to talk about how we might build a color wheel. We talked about Newton's color wheel, but now we're going to build a color wheel in the RGB space, CMY space, that we have come to use a lot with regards to our display and printing environment. When we do that, we're going to put down our RGB primaries first as step 1. We're going to put down our CMY primaries as step 2. And then we're going to put around our tertiary colors. And then we're going to have a color wheel. So then what we're going to do is we're going to have some color harmonies. We're going to show relationships between the various colors. And this is sort of like what artists do and how they base their color theory. So this is a monochromatic color theory. And basically what this is says, for a given hue, if I add some white, I'll get a tint. If I add some gray, I'll get a tone. If I add some gray, black to the color, I'll get a shade. I can also create a visualization, which is what this pie chart is, of hue, tints, tones, and shades. And I created a monochromatic color scheme. And you'll see that this is used in our visualization world quite a bit. I can also do a complementary color. I showed you the purple and green as a complementary color. I showed you the orange and cyan. So let's look at the orange and cyan phenomenon. And this is the particular. This goes back to our tree map. And we're going to see that this is a complementary relationship. Here, I use Tableau Public, by the way, to make this. We also have an analogous color harmony, and that is colors that are next to each other on the color wheel. And so I'm going to show you these colors are all next to each other, and this is what I used to do the bubble chart. Now, lately I've been writing a lot, and if you want to look at Nightingale, I show you in this example. If you look at my, go down to Nightingale, the Journal of Data Visualization, and you're going to find that I've written out in detail a lot of these examples I'm showing you here. There's also another triad color harmony, and that's called 3 colors equally spaced on the color wheel. And believe it or not, we've been talking triads in this lecture. I've been talking about when I talk cyan, magenta, and yellow, that's one triad. When I'm talking red, green, and blue, that's another triad. Triads intend to be very vivid. They're on the outer edge of the color wheel. And so you'll see in this particular example, I actually made them a little duller, add a little bit of gray to each of it to get a little duller final triad color harmony. The tetrad color harmony is 4 colors equally spaced. Some people call that double complementary color harmonies because they're 2 complementary pairs here. I'll show you an example of that. So it turns out that these color harmony concepts are really great for mixing our colors and visualization, but it does not always pass color deficiency. So here is a bubble chart I made. I showed it to you earlier, and guess what? The protanopia and the deuteranopia, it's hard to tell the difference between these bubble charts or these particular circles. And so what I did was realizing that what they call double-coded it. I put text inside each of the little bubbles that describes the particular area the data is from. This is a data set of particular countries, and it describes where each area is coming. I've double-coded it because I know I'm not going to pass a color deficiency test. That's what you do when you're in the middle of a visualization. You got to get creative on it. Okay, so here is a color lovers website. You know, artists often steal from each other. Sometimes they credit, but basically they steal color concepts from each other. And this color lovers website is willingly, artists post their various color schemes. This is my various color schemes. And I've taken color schemes from other artists. You might like this website, because you can combine this and come up with some creative color combinations for your visualizations. It's a really neat community of sharing among each other, actually. I use the word steal lightly. So this is another particular way of looking at color. It's called the Color Gamut Mask tool. It was developed by artists. This is, imagine plein air painters out there with their palette of paints. They want to mask, they don't want to look at the whole range of the color spectrum. It's kind of overwhelming, so they mask off their colors. And this is what you're doing. You're masking off here to create this. And I show you how you can mask off these particular colors and create a visualization with this. I'm going to cover this visualization further, but this is a visualization of broadband network in the state of North Carolina, and who has it and who doesn't with this. And I use this particular color scheme. So there's a very well-known color advice for maps tool called ColorBrewer, and I'm going to assume that many of you have used it. Cynthia Brewer and Mark Harr were the first ones to publish and develop this particular tool. Brewer got funding. She's an amazing geographer. She got funding from the National Science Foundation to develop this tool, and ESRI has picked up her work and basically publishes a lot of her work. So she came up with sequential, diverging, and qualitative color map classifications. Now, why do you care? You care because when Maureen Stone was developing the Colors for Tableau software, she based a lot of her work on the ColorBrewer concepts. And Tamara Munster, in her Visualization Analysis and Design textbook, she bases a lot on sequential, diverging, and qualitative color maps. So let's review this. in case this is new to you, the sequential scheme is optimized for ordered data from low to high. This is a sequential color scheme. The diverging color scheme places equal value on mid-range critical values, so as well as extreme values. So what you're going to happen is you have the color dropping in the center. So she uses either a white or a yellow at the center of her color combinations. Then she uses a qualitative scheme where there's no magnitude differences implied. Oh, they're suited for representing data that is what they call categorical. So let's look at a particular example. This is a diverging particular color scheme. Again, we're going to visualize the household broadband availability of data in 100 counties of the state of North Carolina. This is the color scheme we're using. Now, the visualization turns out to be a little different, right? Because how the data falls is a little different than maybe what the color scheme was designed as. But you're going to see that this is the particular visualization. Now we can use ColorBrewer for information visualization. This is a particular bar chart. Now, I'm going to take it a little bit further. I'm going to ask the question of how can I use ColorBrewer in developing an animation? Now, ColorBrewer was normally developed for maps, but this one now we're going to do an animation. So let's think about, we've got a black and white computational hurricane. We've got a hurricane that we know what it looks like as it time steps in black and white. And basically, what I'm going to do is I'm going to use ColorBrewer, and I'll say, okay, I want to achieve this particular color scheme, the purple and orange one. But what I've got to do is I've got to apply color theory. Because my Visit software tool that I'm using, this is Department of Energy software, is basically going to mix magenta and blue together, and it's going to make the hurricane purple. So what you're going to see go on here is a time step. So I'm going to select this particular color scheme, but I'm going to force my data to make the purple. So what's happening is I'm using complementary and analogous color theory. So I'm going to have some wind vectors, which my meteorologists tell me they got to have the wind vectors to see what direction the wind was going in when the eye of the hurricane happens. So I got to have orange vectors, which are going to be complementary to my blue background, and those vectors have got to stand out no matter what. So I'm going to use a complementary color scheme. Then I'm going to have an analogous color scheme where I'm going to have the magenta and blue come together and mix the eye of the hurricane into purple, and that hurricane is going to evolve. So I'm going to show the evolution of that visualization turn into from a light purple and magenta dots using pointillism turn into the eye of the hurricane. Now, I'm not going to play the video in this particular example, but this is actually how the visualization was done. Then when we looked at color deficiency, we wanted to make sure in case some of our researchers might have a color deficiency. This is, you can see it passed Protanopia, Deuteranopia, and Tritanopia test. I'm using a tool called ColorBrewer, by the way, to look at it, and I'm showing it to you here. Now, I have also recently published a new way of doing this particular visualization approach that I use the Albers app, and you can see I did a little bit of bubbles, and I create a similar concept. You can read that if you want to. So basically, let's take a break. I've talked a lot about color theory here. Let's have a little question and answer, and let's take a break. Okay. Well, is everybody still kind of hanging out? I'm ready to answer some questions if you're ready.
think we got the sounds of silence here. You want to know how they ask questions. Okay, it says, am I going to cover, wait, here are the questions coming in. Are you going to cover an example on how to make a color palette work for color deficient people? Yes, I am going to cover an example. I've also written quite a bit on it, but that is in the second half of this video presentation. There's been a lot of development of color theory of the past century. Is there a simpler step-by-step guide for beginners to start? Wow. Well, I have a book. I wrote a book on applying color theory to digital media and visualization. So I could say to you, Greg, I got a book on the topic. Now it says I can type questions. So let me see if I can type, that people can type questions. So I'm going to answer some things in chat. Yes, try my book. My book. It is, if you want it. I covered that at the end. Of course, I did not think I was going to promote my book on at this particular point in time. So I'm racing right here to find out where my book is. On I know it's on Amazon, and I know it's from the publisher. Let's see if I can applying color theory. So let's see how well I can search this out myself. It was published by CRC Press. Okay, I just got to it. Okay, it's also on Kindle. Barnes and Noble carries it. I'm gonna put this URL on Amazon for people who are Amazon lovers. Okay, let's see. What do I have here? There has been a lot of development of color theory. Am I going to color example how to make a color palette work for color deficient people? Yes, I am. I am going to cover this. I've written quite a bit on it recently in Nightingale, and I have some examples at the end. My Nightingale articles cover it. The tools that I use are something called CoBliss, Color Blindness Simulator, and Adobe Color has some great tools for how to handle color deficiency. Let's see what else I got. Anybody have any other questions? So how long are we supposed to go to 11? Okay, I think we hit 11. Oh, well, wait. I'm doing it by my time. Wow. I can. Hey, everybody, if you want to take a break early, that's great. Want to go get your lunch? I would do that. Or get a coffee, late breakfast. Wait a minute, you have a question here. I think that one of the problems is people don't know how to ask a question. All right, you can type your question here on YouTube or on Discord channel. Try my butt. A lot of people don't know how to ask a question here. Looks like questions should be asked via Discord. Or YouTube. Or YouTube. Okay. All right, who's Nina? Okay, thank you very much, Nina. Okay, somebody's having trouble. Manually refresh or something. Boy, there's a big delay from what I do into YouTube. There's a delay. Yeah. Right. Well, shall we just call it until what time we come back? I will stay on, but since I'm not getting much. Okay. $50, right? Okay, bye-bye.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
We propose X-matrix, a novel method for random forest interpretability. From a random forest model, a logic rule is extracted from each decision path on every decision tree. Once the complete set of logic rules is obtained, visual representations can be built for global and local explanations. X-matrix, making random forests interpretable.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
How do we represent remote users in synchronized visualizations while supporting divergent exploration? We present cursors, the basic unit of user representation in a collaborative visualization. They can vary significantly in appearance, as you can see. Cursors enable collaborative interaction techniques, such as peeking, tracking, and forking. To learn more, please read our paper representing real-time multi-user collaboration in visualization.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the CN model is not easy to understand. We introduced the Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the Explainer, users can progressively explore the CN model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
CMYK is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMYK can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMYK provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Druid.js is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Druid.js is a web tool using DR. You just need to import Druid.js, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Magnetic reconnection is a ubiquitous and complex physical process that occurs throughout the universe. Locally, this process is observed when the solar wind interacts with the Earth's magnetosphere, causing magnetic field lines to break and reconnect. One of the results of this process can be seen from Earth as the aurorae. In our talk, we introduce scalar field topology as a method to identify and analyze features in 2D magnetic reconnection simulations.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the tasks to your requirements at the interactive testing section and observe them at the testing evaluation section.
Information about vulnerabilities helps defenders prioritize what they need to patch, but this information can be difficult to interpret. In this paper, we support interpretability using a focus-in-context approach to visualizing vulnerability data, including a clustering overview, plots that enable filtering based on severity, and explanations of text features and descriptions. We invite you to read our paper to learn more.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Hello. Student competition is intrinsic to the pedagogy of cybersecurity education. At RIT, we have observed that the collegiate penetration testing competition and other related competitions are missing a key element: visualization. In this position paper, we provide an architecture and plan to create compelling experiences for participants and spectators. In doing so, we can potentially attract new talent into the field.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
Programmers often make mistakes like this. A VIS function is incorrectly called with a string. A programming language can catch such mistakes early on, but for this, it needs a type system. We present Typical, an interactive visualization tool for programming language designers. Typical allows them to explore common function type signatures and helps create a type system.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deep-water asteroid impact simulation ensembles.
Deep learning models have become ubiquitous, but we often lack interpretations for their decisions. We developed a visual analytics system to interpret models that perform multi-class DGA classification. For each layer of the model, we visualize clusters inside its activation data, showing how classes and clusters relate to each other. In addition, we provide a decision tree to explain how these clusters are constructed.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We find that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present a flexible and easy-to-use software infrastructure for interactive rendering of large-scale display walls, either from on-site or from remote cluster. The display servers can easily be configured to support a range of typical network and display hardware configurations. The client library provides a straightforward interface for easy integration into CPU and GPU renderers. We also demonstrate this framework for use in deploying low-cost alternatives for display walls.
After determining the departure timestamp, the experts then moved to verify the recommended shuttle stops and routes. Note that ShuttleVis recommends the default shuttle stops and routes based on the metric of average distance. Then they observed that in our cluster 4, the system recommends Hejianjianyuan as the shuttle bus stop, but the experts identified that another drop-off spot Panshanhuayuan is located in the middle part in this regional cluster.
Predictions made by machine learning models can be hard to understand. Counterfactual explanations explain model predictions by telling the users how to obtain the desired prediction with minimal changes to the input. We introduce DIS, an interactive visualization system that supports counterfactual-based explorations on individual instances and data subgroups. Please check our paper for more details.
In this paper, we investigate design choices for choropleth maps by domain experts. We tackle 2 research questions: how do domain tasks influence the design choices, and what equal error projection is preferred. Through a survey, we collected 40 choropleth maps designed by 20 social scientists, and our analysis suggests that the choices vary across tasks, the projection was most important, and the equal error projection was preferred.
VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
Interacting with large datasets could be painfully slow. We can reduce the latency with faster backends, but that's not always attainable. Here, we investigate a solution that only leverages techniques on the front end. We propose interaction snapshots, where users can view the results at a later time. We found that users experienced much less frustration and were able to complete the tasks faster.
DVR has always been from considerable interest to the scientific community. To this day, traditional desktop setups are the gold standard. However, what if we could utilize DVR in virtual reality? Now you think, VR and DVR are so computationally expensive, how is this even feasible? Come to my talk and we present you a straightforward solution to visualize volumetric datasets with high refresh rates on VR devices.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduce a scalable and flexible way to interactively build hierarchical topics.
A Morse-Mean complex is a topological descriptor that captures the gradient flow of a scalar function. The best-known approaches for its computation incur large runtimes for bigger datasets. We address this gap by introducing the first completely GPU parallel pipeline, which achieves speedups of up to 7x, with our individual algorithms attaining speedups of up to 129x and 4.5x.
In this talk, we introduce call flow,
an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale scientific applications. CallFlow visualizes the flow of resource of a program execution as a Sankey diagram to detect performance bottlenecks in parallel codes. CallFlow simplifies these calling context trees based on semantic information by constructing supergraphs.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
Evaluating alternative interpretations is an essential part of complex sense-making, but the resulting ambiguity is rarely considered in the design of visual analytic systems. Avalanche forecasters rely on sparse and human-produced data to assess avalanche hazards, often resulting in ambiguous interpretations. We used simple glyphs and unit visualizations to specifically consider and support ambiguity in the avalanche forecasters' sense-making processes.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
We present a method for real-time ray tracing of stream tubes for fluid flows and diffusion tensor MRI. Rays are traced through a sparse voxel lock tree until they intersect leaf nodes which contain tube segments. This checkerboard pattern indicates voxel boundaries. Within leaf nodes, we can ray trace straight tube segments or ray cast curved tube segments.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Forensic investigation of file system metadata is a difficult and time-consuming task that requires deep expert knowledge. Following a user-centered design, we implemented an analytical tool to guide analysts during a security incident investigation. The evaluation proved that the tool could significantly improve the efficiency of disk exploration, even for less experienced analysts.
Analyzing urban heat island phenomena,
which cause higher temperature in cities, require us to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Syringe graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign allurance through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the syringe graph layout optimization. The result shows that our algorithms perform better than the others.
Smartwatches can track a wide variety of data. We are interested to learn which type of data people consume and how it is visualized. To find out, we conducted a survey with 237 participants. We found a predominant display of health fitness data, with data mostly displayed as icons with text. Based on our findings, we discuss opportunities for visualization research on smartwatches.
The visual analysis of large-scale data from complex systems such as electronic health records has become increasingly prevalent, but can be prone to a variety of selection bias effects. We introduced dynamic reweighting, a novel approach to selection bias mitigation that helps users craft bias-corrected visualizations. This approach is implemented in the Cadence Visual Analytics tool, which provides visualizations of and control over the dynamic reweighting process.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
Do these three essays construct their argumentation similarly? Where in this table of argumentation data from the previously seen texts can I find certain argumentation patterns? Do these three argument maps depict the same argument? We have developed a visual analysis system for argumentation in essays that can answer these questions at a glance. You want to know how it works? Come to my talk.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
Data lakes can contain millions of tables. Data portals have tools like keyword search to find data sets, but often researchers don't care about semantics, but rather structural metadata. Can I find a data set with many rows, few columns, and preferably a high number of unique values? Log Perspective visualizes structural properties based on the user's needs and helps researchers fish out data sets with appropriate structural properties.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results, for example the Monet-based brush and the CN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
Hurricanes, air pollution, forest fires, urban sprawl, ocean plastics, politics, traffic jams, and pandemics. So many of our modern challenges are geospatial, and so much of our big data is geospatial. How is the VIS community addressing needs to visualize and analyze this data? Our review examines IEEE VIS's recent contributions to geovisualization and geospatial analysis.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
A dynamic graph models changing relationships between entities over time. In this work, we present multi-scale snapshots, a visual analytics approach to provide an overview of a dynamic graph at multiple temporal scales. The approach consists of 3 steps: creating multi-scale temporal summaries, applying graph embeddings, and the semi-automatic visual analysis. The combination of these steps lets us visually explore how temporal and structural properties affect the overall dynamic graph.
In human brain mapping, atlases are indispensable to scenario imaging experts. While many of these atlases capture general trends over large populations, they fail to capture subject-specific complexity of brain organization. We propose Pragma, a tool for interactively deriving individual-specific brain maps from established atlases. Pragma supports within and between parcel analyses to help experts make decisions during the parcellation process.
Text alignment is a fundamental technique in many text-related domains. In this survey, we cover 3 text alignment scenarios: collation task, text reuse detection, and translation alignment. On the basis of those scenarios, we reviewed the existing text alignment visualization approaches and discussed their advantages and drawbacks. We finally derived design implications and shed light on related future challenges.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
Magazine-style narrative visualizations can be challenging due to the need to go back and forth from the text to the visualization. We use eye tracking to monitor which sentence is currently being read and trigger visual links between that sentence and the corresponding data points in the visualization. Results show that the gaze-driven links increase comprehension of the documents without hindering reading time.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the last structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CIE Lab, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
We present StratGraphics, an approach for designing data-agnostic and fully reusable visualization templates. StratGraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
In our paper, we address the problem of navigating complex multiscale and dense environments, such as these molecular models. We present a technique for browsing a model by clicking on textual labels, which we call hyperlabels. This allows the user to intuitively navigate the hierarchical organization of the model. For more details, read our paper or watch the talk.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
Nowadays, online services are used for all kinds of activities. Strategies to increase the situational awareness of personal data stored by online services are needed. We present Transparency VIS, a visual, interactive web application. It allows common internet users to explore their personal data exports, which can be requested from online services like Facebook, Google, Instagram, or Twitter. Feel free to try it out online.
Hi everyone, let's get back into color basics. We've had a little break and now we're going to talk about some tools. As a reminder, earlier we went over color models. We talked about color theory and color vision. We looked at color gamut and spaces. And now we're going to talk about color tools. Now there is an item I want to digress to. I was listening to my first video and I covered Trichromatic Theory of color vision, and I realized that I forgot to mention to you guys that not only are there photoreceptors in our eyes when it comes to color vision, when our cones perceive all this red, green, and blue and the various entire range of colors, it goes from our eyes into the optic nerve. And a lot of Hering's work in terms of opponent color theory really dealt with the process of taking color vision and moving it into the color vision from our cones and moving it into the optic nerve. And this is where he came up with these concepts in terms of opponent color theory. Anyway, I've covered that, so I want to make sure that you knew that. I also neglected to mention that Helmholtz was threatened by Hering's observations, and it would take many years until the 1950s, until Hurwitz and Jameson showed that the two operated together. But anyway, that's all history, so let's go and look at the present and think of a tool like VIS Palette. VIS Palette is this really cool public tool that's available to you. It's a free web app for making color suggestions and information visualization, created by Elijah Meeks and Susie Liu. It's possible to enter colors via ColorBrewer, ColorBrewer, and Chroma.js, your various visualization tools. You can also use Hex, RGB, and HSL values. It provides color deficiency functions when viewing results. And I give you the website. Now here I'm showing you how you can take the various ColorBrewer color themes and enter them directly into VIS Palette and see what the visualization options might be to you. This is the color map I use for actually our hurricane visualization, and this is what it would look like for various information visualization solutions. Now I want to move into something with regards to how to use VIS Palette for if you have a color scheme that you built. Let's say I got this tetrad color harmony. Now, I use a Palladium color scheme designer for creating this particular color harmony, but I want to see what it would look like with various visualization capabilities or options. And what you can do is enter those colors into VIS Palette, and you can see, and then VIS Palette can also do Proto-No-B and Deuter-No-B color vision checks. So this is a really handy tool to use. I use VIS Palette a lot. And it's free. Now, Adobe Capture is a tool that I'm going to highlight a little bit further in this discussion. And Adobe Capture allows you to go out into the world and use your mobile device to capture a scene. Here I've captured something in a particular forest area, and I've got a series of greens. And I'm using VIS Palette here to see what a particular green color scheme would be if I did that. I believe that that's an analogous color scheme I've got across in there. Now let's go to Adobe Capture. So Adobe Capture is actually a tool that's on your mobile device. Adobe Color is the web version of the tool, but the actual mobile app is called Adobe Capture. Both are free. Download them. And also Adobe Capture works on the iPad. You can basically take an image that you've got on your phone, run it through Adobe Capture, and get a color scheme from it. There are a lot of times you can build some creative color combinations that you might not normally come up with, but that Mother Nature kind of came up with. So this is what I'm doing here. And then this is a particular color scheme. Now, I wrote an article for Nightingale where I went through all the various different color schemes that you could get from this particular image, and I covered all the different color harmonies available in Adobe Capture. And I'll let you read that. But what I've done here in terms of VIS Palette is I've shown the palette with a monochromatic, green monochromatic color scheme, going through the particular visualization potentials here, and then I've done a check in terms of what it's going to look like if there's a color deficiency viewer. I've got Protanopia or Deuteranopia, and the VIS palette provides you both of these. Now this is a nice way of checking any kind of color scheme that you might find or you might have on created on your mobile devices, and that you might like to check real easily with VIS palette. So I really like this tool a lot, and you'll see in a lot of my writings that I like to combine it with other tools like Adobe Capture and Adobe Color. Okay, now I want to cover this particular example. This is an example I did years ago. I first wrote about it in 2012. It's a supernova visualization. It was done on a high-performance computer system. It's looking at the death of a neutron star. It's called a supernova, an explosion out in space. And basically, we did this visualization. I was at North Carolina State University. I was running a visualization center at the time that I did that. We had it in black and white, and we colorized it. We used a tool called Insight, which is a very powerful tool today. It's still available today for creating the visualization, and I was responsible for colorizing it. And basically, I first wrote it up in terms of applying artistic color theories to visualization, described it in a 2012 article I did in a special publication that was dedicated to an amazing visualization guy called Jim Thomas, who developed a lot associated with visual analytics and one of the components of the visualization conference here. So anyway, here's the visualization. What I've done in terms of the supernova is I've combined an analogous color map of green, blue, and yellow to create the yellow center of the neutron star. And then I've wanted to emphasize the edge. In terms of visualization, our scientists told me that we needed to have the edge visualized, and I put purple around it. And it came off pretty good. This visualization was extremely well received. It won something called, in 2008, the best overall image and best scientific image at Insight's user group. This is really great. Now, I happily published in 2015. Then I got into looking at color deficiency further. And I got hold of the Coblis tool. And one day I'm saying, hey, you know, how good is this visualization? Well, guess what? It fails the color deficiency checks. I've long since left. In 2013 or 14, when I did this work, I'd long since left NC State University and long since left this lab. But I wanted to tell you that you can win right and left, but slightly lose, because this is not workable in terms of, if I was doing it today, I would not use this particular color scheme, because if you have Protanopia or Deuteranopia, you cannot tell what's going on at the top. You'll see it goes into white, and you can't differentiate that. And if you have Tritanopia, you can't differentiate some of the colors. But anyway, live and learn. I just want to make sure that you know that I may talk to you about the mistakes. Chances are I'm talking to you about things that I've done. I made the mistakes. Anyway, so I went back and I want to say, hey, what's going on here? So I'm looking at the color deficiency. I'm using a tool called Palladium. It's a Palladium color scheme designer. It's really developed for people who are graphic designers. It does have color deficiency built into it, and so I went across and I looked at the color deficiencies. Since I actually used this particular Palladium tool, it was around in 2009. I used it for building the color scheme. I wanted to see whether I could have found the color deficiency if I'd known about it. And I went in, I looked at it, and it looked like the complementary color harmony passes the color deficiency test. So the yellow and the purple would have passed. But it's the analogous color harmony that kind of fails the deficiency check. You're going to see, you can't really tell the greens and the yellows apart from one another if you have Protanopia and Deuteranopia, and that shows up in the visualization. That's why some of the stuff doesn't appear. And then if you have Tritanopia, you're not going to be able to tell the blues and the greens from one another. Anyway, so you can sort of see the results. You might like to use this tool called Palladium. It, interestingly, is actually based on the red, yellow, blue color model, even though it displays an RGB color space. But it's a really cool tool, and you might like it. But use a color deficiency capabilities in the tool. Don't make my mistake. So now I want to step a little bit beyond the digital world and talk a little bit more about the physical world. Earlier, I really talked about this idea that RGB color space, when you take a visualization, created in that space, which many of us probably do create our visualizations there, and you print it out, or you go into cyan, magenta, yellow color space, there's some real problems. And yeah, I wrote this up in Nightingale, and I thought I would go over this particular case study for you. It uses a tool called Adobe Color, which is probably historically, is one of the first digital color assessment tools around, and it's still free today. So let's go through this example. In the particular article, I talk about this split complementary color harmony that I built. So that would be yellow is the key color. That's the primary color I started to build the harmony in. And then the split is the direct complement would be a sort of a blue range. Remember, I'm in an RGB color space, and we talked earlier about how yellow and blue are complements to each other. So the split complementary on either side, which is a color on either side of the primary complementary, is going to be a bluish, cyan bluish combination, and then a purplish combination. So I'm in Adobe Color, and I'm designing this color harmony, and it's looking pretty good, right? So I'm combining a key color with the two colors on either side of the complement. Split complementary, I'm liking it. So I'm going to try to do a bar chart type visualization, and basically I'm going to have a yellow line, and then I'm going to have my data that's going to be in these basically in these blue and purple ranges. Okay, so that's what I'm going to do. And I'm going to show you that a little bit later. Now, guess what? The new functions of Adobe Color, this is very new. That just came out around June or July of 2020. We're talking really new. So that basically, they have protanopy, deuteranopy, and tritanopy functions. And when you put a color scheme in, if you ask to click on accessibility tools, it will immediately tell you there's a conflict, that the tools the two colors cannot be differentiated. It's saying here A and D. So where A is the color on the far left, and D is like the purple, and it's telling you, and you can see that line across here, that those two colors are not going to be easily differentiated by someone with a deficiency. So it basically allows you to correct it. You can correct this, and basically, if you do it right, you'll pass the color deficiency. So that's what I've done. I moved my colors over, and I've now got a colorblind safe deficiency. It doesn't say, it uses color blindness rather than the word color deficiency. But a colorblind safe color theme in Adobe Color. So now I've got this nice color combination, color theme. And now what I want to do is I want to continue with this idea. I told you what I'm going to do is I'm going to build a color data visualization, and I'm going to basically have a yellow line, and then I'm going to have this bar chart where I've got the cyan blue up against the purple as a combination here. That's pretty good deficiency. Now, deficiency, how can I say deficiency? That's a pretty good visualization. It's a pretty classic visualization. Straightforward combination. Now I'm going to run it through some deficiency test, and what's going to happen is sort of Adobe Color had already alerted me to it. I tend to like to go ahead and use CoBLIS. CoBLIS, Color Blindness Simulator, is a tool I like to use on my actual visualizations, because I feel like even though Adobe Color has given me the color differentiations, I want to see what's really going on inside the visualization, because there might be some things going on with the final presentation in the 2D and 3D space that are different from the color swatches. So I'm running this through CoBLIS, and I already sort of know that I've had to be careful and make sure that the blues and the purples, if you have a deficiency, one's going to be a light blue and one's going to be a dark blue. We fixed that earlier in Adobe Color, and then Tritanopia is going to be safe. Now, so we have an improved, I call it a yellow divide, improved yellow divide bar chart visualization. And you can see I'm using Cobbliss right across in here. So now what I'm going to do is I'm going to print this thing. This is going to go into, let's say it's going to go into an annual report. And I'm going after printing. Now, Adobe Color gives you some color modes and codes that you could use. You can use red, green, and blue. We covered that model earlier. HSV, CMYK, and Lab, CIE Lab as the other color space. It gives you all these particular combinations that you can use these color modes. So we're going to probably go to a printer, so we're probably going to check CMYK. Now, I told you earlier that there's a little challenge. There's a chance this thing is going to look faded, right? So here's what it looks like. What I'm doing here is if I go into, basically, I can go into Adobe Acrobat, and if I ask it to tell me what it's going to look like if I go into CMYK, so I can look at it even online, see what it's going to look like in CMYK portable document format. If I look at it, it's exactly what we talked about before. I have lost the vivid nature of the colors. The combinations are much duller than what I wanted. Now, this would I went through this experience myself when I produced my book. I'll highlight my book a little bit later in this lecture, but when I produced my book, I had to look at the colors that I originally had on the screen and see what it was going to look like in my book, and this is a particular example. Now, if you're doing this big annual report, your bosses might not love the fact that you just got some really dull colors there. So they might say, fix it. Let's just make it real simple, fix it. And they say, well, it's going to, you say back, it's going to cost you. Tell me how much it's going to cost, but fix it. So what you're going to do is you're kind of consider Pantone. I talked earlier about Pantone processes and for color printing and color inks. Basically, what you're going to do is rather than using CMYK and forcing it to make the colors with various cyan, magenta, and yellow paints or inks coming out there, what you're going to do is you're going to say, okay, for my color printing process, I want to specify some Pantone colors. I'm going to specify my blue, yellow, and my purple, my combination here. And Adobe Color will give you those Pantone colors that you can specify. Remember I said the Pantone matching system values. You've got to be able to talk that to your color printer and to your designing people at that shop. You better know what those Pantone colors are. So, I mean, they can mix them for you, but your boss is going to want to make sure that you've got his company's or her company, we'll say her company's well represented, and that her visualization person can go down there and specify the colors. So you've used Adobe Color and you've got your Pantone color specified, and that's what you're going to do. So this is what you're going to specify, and it's going to cost. And you're going to go back and you're going to say how much your printer says. Well, this is the combination of what it would be in CMYK, and this is what it would be like in Pantone. You're going to present the issue, and your boss, like I said, it's going to be she running the company. She's going to make this decision as to whether you're going to use this printing for the annual report. Okay, so that's the particular case study I was highlighting here. Now I want to highlight Pantone Connect for you, because in terms of visualization, this is a very, very new tool. Pantone Connect also came out around June and July 2020. And there's been a lot going on in the color field over the last 6 months. A lot of changes, a lot of new tools have been improved and revamped. Pantone Connect, historically there was a tool called My Pantone. Then it went to Pantone Studio, and Pantone Connect is their newest version. And basically it allows you to image capture and come up with Pantone colors, or you can use color harmonies like we covered earlier and come up with color themes. So I'm going to walk through both particular options. You'll see what I've done is Pantone is designed for the designer community, and I'm talking about people who do fashion. I'm talking about somebody like Michael Kors, who comes up with color combinations. He uses Pantone values. This is really true. You're going to find out that athletes know their Pantone color for the particular team that they're on, because it's important, because they have to know what their color is going to look like on their t-shirts, on their uniforms. They need to match what it's going to look like in their street clothes, so they know their Pantone color. But anyway, that was a little digression there, but I was just trying to get you ready for the fact that if you're a Viz person, it's good enough. It's good to know how to speak the Pantone language. So anyway, I want to walk through this tool, but in order to stay in the Viz world, we combine this tool with tools like Viz Palette and CoBliz to do our color deficiency check. All right, so now we're going to look at selecting a key color in Pantone Connect. I have just written this up. I'm recording this very early. By the time you guys see it in October, I'm hoping that Nightingale will have published this article maybe in September, but it's just hot off the press. I hope you can read the article for further details, but anyway, you're going to select a key color, and here I'm going to select a Pantone. It's kind of a pinkish red combination that I'm going to select, and it's called Pantone 2029C, and that's how I'm going to read my color. And now I'm going to go, I can either have a web app or mobile app. Now I'm using the mobile app in terms of the illustrations here. Now I'm going to select color harmonies, and this is going to be a little review for us. So the Pantone color harmonies will come up. Now, interestingly enough, the Pantone color harmonies that come up do not have a color wheel on them. There's no little color wheel. What you're going to get is a bunch of color swatches: analogous, complementary, monochromatic, split complementary, triadic, and tetradic. So I added the color wheel, and I do know the people with X-Rite and Pantone, and I've said, you guys, you really, and it is guys, it's two gentlemen, you really need to add a color wheel, because people don't know what the word analogous means. They don't know what the word complementary means unless they're looking at a color wheel in terms of that. Of course, they might be Googling and trying to figure it out, but there are going to be a lot of people that don't know. But anyway, what happens is Pantone gives you a set of color harmonies, and you guys have taken the first part of my course, so you know what analogous is: colors next to each other on the color wheel; complementary, two colors opposing each other; monochromatic, colors that one color and with tints, tones, and shades. Yeah, I just colored split complementary, the color and then the two colors on either side of the complement. Triadic, remember we colored that earlier, that's three colors. And tetradic, double complementary. See the advantage of taking the course. So anyway, that's going to be my forthcoming writing. You can get this in detail. Now, in terms of doing this visualization, I wrote this up. I have a particular example that I'm going to build an area chart, and I'm going to show you that area chart. My client wants the colors to be distinctive. In other words, a split complementary won't do, because there might be implicit connotations associated with having two colors that are near each other and one color that's across from each other. Or tetradic, if I do tetradic, I got to find another fourth color in the color wheel. I don't want to do monochromatic because that's a gradual progression. That's like that sequential stuff that ColorBrewer is so strong in. I want four distinct colors. So I don't want some color that's built up with tints, tones, and shades. And I don't want just a complementary color, one complementary color, and then have to find another complementary color. Actually, but maybe that's an idea. Maybe if I have a complementary, tetradic is going to solve my problem. Tetradic is going to give me four colors that are distinct and spread apart on the color wheel from each other. So that's what I'm going to choose. So I'm going to select a tetrad color harmony here. And then Pantone, because Pantone Connect is kind of powerful, it's going to give me the sRGB value. It's going to give me the hex value, which I'm going to need to enter into this palette. And it's going to give me the lab values as well, if I need that for a particular color tool. And you might need that for some advanced visualization capabilities that you might be doing. So it turns out Pantone Connect, although it's designed for the designer world, is kind of working pretty good for the visualization world. And now you sound like a designer because you're able to talk, you're able to give your PMS color values, and you're able to talk that lingo with your graphic design team and with your color printing team. Okay, so anyway, here's a tetrad color scheme. Now I know it. Now I'm going to build, I like to use Apple Pages and Apple Numbers for visualizations like these. I don't know what you want to use. You might like to use your Google Charts, whatever you want to use to build a particular chart type visualization. This is an area chart, and basically what I've done is I've entered the hex codes in, and I've colorized the area right across in here as a visualization. So you're going to see it's distinct colors. Each color is pretty distinct, not weighted. The other way you could call this, if we want to talk ColorBrewer language, we can call this a qualitative color scheme. Basically, I'm trying to build a qualitative color scheme. I don't want a sequential one. I don't want a diverging one. I want a qualitative color scheme. And the tetrad color harmony is going to give me a good option because I also have 4 data elements. If I had 3, I could do the triad, but I have 4 data elements. So that's what I've got here. All right, now what I need to do, because Pantone Connect's not going to give it to me, is I've got to go do some color deficiency checks. Now, if I'd used Adobe Color, I could have checked the color swatches, but I'm in Pantone, and I know I'm going to go for high-end printing, and I want to stay in Pantone because I want to work directly in knowing my PMS values for what it's going to be like, and the big poster that comes out, or the big annual report. So I'm going to use the color blindness simulator, CoBLIS, another free tool. I'm going to take a picture of my normal visualization, and I'm going to run it through CoViz, and I'm going to see what Protanopia, Deuteranopia, and Tritanopia tell me. And boy, am I ever lucky on this one. This is really luck because Pantone Connect wasn't designed to support color deficiency. But it just so happens when it goes through, someone who has deficiency will see those colors as different from each other. So I'm not, if it didn't pass, I'd have to go back and find some other kind of color combination to make the thing work and go back and forth to pass my CoBLIS checks. All right, so that's what I got. I'm doing pretty good here, looking good. So now that visualization's in the can. The boss thinks I know what I'm doing. Says, okay, all right, now I want you to come out with something different. So I go, okay. So I go out to my garden or whatever. This is for my garden. And I just snap a picture and I put it on my mobile phone. And then I move it back in through Pantone Connect, and I get it to tell me the kind of colors that are out there. And this is a particular color palette I got. It's got some nice greens. Now, you know, when you're dealing with garden visualizations or when you're dealing with landscaping type stuff, the neutral color is the green because there's a lot of green, and the colors that pop out are the flowers or the floral arrangements. That's going to be yellow and pink and those types of things. So you're going to have a lot of green combinations with it. But, okay, Pantone Connect extracts the colors for me, tells me what the values are. Here's I got the values now. I know. And I'm going to bring this in. I'm going to say, okay, I got a distinctive color combination, and I need to know what's it going to look like with some visualization capabilities here. So what I do is I run it into Viz palettes real quick. My bosses haven't told me what kind of visualizations they want me to do, but I know I got an area chart, I got a tree map, I got various color combinations, I've got some turkey plot, not turkey, but Thanksgiving, but turkey plots. I've got some various statistical graphics here, and I got Protanopia and Deuteranopia tests I've run across here. Oh my gosh, I'm really lucky because they passed those tests, and I'm still doing okay. But I do have 2 different greens. So, you know, I'm ready. I got my handy dandy new color combination, and the boss says, 4 distinct colors. I told you. I like 4 distinct colors. I don't want to do it that way. The 2 greens are not going to work out. We're not going to accept that. You got 20 minutes, and you've got to find me another color. Oh, thanks, guy. So I'm in Pantone Connect, and I go real quickly, and I go, okay, I remember that tetrad combination. You got to have a little bit, you got to remember your past a little bit. If I'm going to pick that pink, and I'm going to go in there, and I'm going to find something like that purple combination from my prior work. And I go, oh no, I kind of think that blue one might look really good. So I picked this Pantone 2123C from my Triadic Color Harmony. So what I've done is I pulled that pink 190C, Pantone pink 190C, and I've asked it to give me some color harmonies because I got to have 4 distinct colors very quickly. And it gives me this nice purple Pantone 2123C, and I think that's kind of different. It's going to be a little different. I throw it together. I save the name. I call it Garden Plus. Got to go back and meet with the boss now. I go in. I check my color capabilities. I use VIS palette real fast. Put it up there really fast, and I go, yes, that's fine. Fortunately for me, it passes color deficiency. I'm real lucky. I got 4 distinct colors. I'm doing just terrific. So I go out there and I make whatever visualization I'm supposed to be making for these particular projects. All right, end of that story. Now let's look at another thing that Pantone Connect can do for you. So we're going to go back. We got our area visualization, but we never ran it through. Now pretend we never ran it through Pantone before. And our boss comes in and says to us, hey, I really like that area chart visualization you did. I think you did really good. And I think this data is really important. So this visualization is going to be in our annual report. Now, I need you to go work with the graphic design team. Oh, no, I'm a visualization. No. I want you to take your visualization over to the graphic design team. And I want you to make sure that it looks really good, get the quality transferred. Cost is no option because this is our big report. I want you to make sure that you got that visualization looking good for when it's printed out. So what you've got to do is you go, oh no, I got to talk to the graphic designers for making that report. Okay, you're going to run it through Pantone Connect. You're going to take your visualization through Pantone Connect, run it through the extract function, and it's going to give you some Pantone colors. Why? Because you're going to have to talk that language to those graphic designers. So now you've run it through and you've gotten some Pantone colors. But it turns out that it didn't get that blue color when it ran through initially, So you got to manually, you're on your mobile device, you got to manually position those sensors so that it picks up that cyan color. I'm using cyan and blue interchangeably, shame on me, but it picks up that cyan color. And now you got the color palette, you got the cyan, you got the lavender type purple, you got the salmon type color, and you got your green one. And now you're able to go talk to that graphic designer about the Pantone inks that they're going to use in that annual report. Now, just for fun, just because we're kind of geeky about color I want to see whether the extracted colors that I ran through from my actual visualization example match the colors I originally designed from. So area chart colors is what came from the extracting the colors. Pastel is the color palette the theme I carefully worked through. And that's that combination here. And I am really lucky because the colors match up. So Pantone Connect is a pretty good tool. It is giving me the same values in terms of the final area chart product against the actual pastel that I designed. Okay, so now I want to talk about some color and visualization research tools. There are 3 recent ones, and now after my course, there's going to be an advanced one that talks about other color tools. And they may cover some of these, but they may specifically cover color-gorical, and they may cover color moves. But I'm going to tell you how I use them. I have a little fun with these tools. So I'm going to talk about how to colorize photos. That's another research tool work presented at SIGGRAPH. I'm going to cover color-gorical, and I'm going to cover color moves briefly. But it's just my kind of enjoying the tools. So colorized photos tools is really getting into this deep learning, machine learning type stuff we've got. And basically, the idea is, can you use deep learning to automatically colorize black and white photos? What this paper did was basically took some of the great photography of Dorothea Lange, ran it through their particular software, and Dorothea Lange took the photos in black and white and is saying this is what she would have colorized. At least they were careful enough not to run some Ansel Adams one. Now, how are they able to do that? Because you're saying, hey, these guys are artists. They're able to do that because Dorothea Lange did that work during the Depression, and she was paid by the federal government. Anytime, some of you know who work at DOE, other types of government labs, when you create an image for them, it's in the public domain. So anyway, these gorgeous photographs that are very, shall we say, historic, extremely well-known images are in the public domain, and they went and colorized them and said what they would look like. And then they published this paper 2016 at, in a European conference, and then also at SIGGRAPH. And I worked with them, got a hold of this tool. I went and saw it at SIGGRAPH 2016, got excited. I thought it'd be really cool to try to see if I could do something in visualization with it. So here's an experiment I did. I went out, I got it, so 2017 SIGGRAPH. I went out that autumn and went and took some pictures of pumpkin squash stacked on top of each other. Original photo image there. Then I converted it to a black and white image, got the grayscale, kind of used some of Ansel Adams' zone system to really get a good black and white photograph of it. And then I went and pushed it back through the colorized photo software to see what it would look like. And you know, it did a pretty good interpretation of it. So I was kind of impressed. I mean, it's kind of reliable. I thought, hey, that's not too bad. Now, I have since in my blog, you will see that I use this colorized photos tool a lot, and I have since shown you some limitations and some difficulties. Now I'm going to show you one with regards to visualization. So this is some deep learning color mapping. Here, I've got my Albers app, and I produced a nice little visual display or colorization, shall we say. I've colorized that app, and I've again colored it and taken it into a black and white. I colorized it, then I took it with the Albers app, then I took it into a black and white photograph type image, high quality, again, using some principles from the Ansel Adams zone system. And then I went and ran it right through the photo colorizer. And you'll see that it came close, but it put some yellows in there that weren't ever in there. It put some combinations. And if you follow my blog, you'll see there are a lot of examples I go through. So you got to be a little careful if we're going to automatically use machine learning to colorize data. Now, maybe we wouldn't care if we have to compare, because maybe in a lot of situations we don't have to compare the final product from machine learning or deep learning with the original, but there can be some differences in the interpretations, and that's what I've been sort of looking at with regards to this. But it's a powerful tool. Very interesting results. So that's kind of what I did here. Another one I did is, this is another Albers study I did with some circles. Then I pushed it through the photo colorizer, took it into black and white first. Excuse me, I took it into black and white first. Then I pushed it through the photo colorizer. And again, I got a new piece of art. I got a new kind of interpretation. Interesting how it kept some of the yellow. It recognized some of the yellow, but it had a little bit of difficulty getting into the purples and the pinks. It was a little challenging. You can look at it two ways. You can either accept that, or you can say, maybe we need to work on the deep learning algorithm here. So now I want to cover a tool that was presented in Baltimore, ColorBrewer of 2016. Connor did the work. Karen Sloss, she is probably going to cover this in her color tutorial that she's part of a team of doing. But this is a particular automated color selection tool. When it is based a lot on CIE Lab. they're going to describe it better than I can do, but I used this tool and I came up with some nice little color maps here. I thought they were kind of interesting. It's not based on some of the color harmonies I've covered earlier in this course, but I like the kind of color combinations. And so I picked this one. I thought it was kind of interesting. And I went back to my cool thing. VIS Palette takes direct categorical values that you've got, and you can move it into VIS Palette. I did it, and I got some nice visualizations. Now, this is what they actually designed VIS Palette to be able to do, to be able to take a categorical palette and push it through VIS Palette and see what various visualizations might look like. I liked it. I kind of like the tree map one a whole lot. So I took that, and then I also made sure I did my color deficiency checks just to make sure categorical doesn't have an immediate color deficiency checks, but thank goodness VIS Palette does, so I'm checking. And so I got a nice little flow here, automated generated color theme, entered into VIS Palette, checked for color deficiencies, and then final results. And that could make my boss happy again, because that's going to be a different kind of color combination than I probably would have even come up with color harmony. So categorical did a neat solution for me. Really great. So now I want to talk about color moves. Now, Francesca Samsel is probably going to cover this one a little bit in the advanced color course. And I basically love to use this tool. It's a web-based tool for interactive color exploration, and I just love this tool. So this is some work that I've actually done from some actual serious scientific visualization. I've taken some work in here and built basically your image processing. So you're entering your tool. It comes in sort of a green-based color. She'll show you that as an example. And then you can use the various colors along that are shown, color palettes that are shown along the left, and build and colorize your image processing tool and highlight various things in the fluid flow analysis. Then there's a nice one that you could take in some satellite data and those types of things and come up with some interesting combinations. I kind of like that. Now here's something I use a lot, and you're going to see in the blog. As you know, you can tell I kind of like the Albers app. So I like to take and use color moves just for the fun of it. I like to take it into an Albers app visualization or a color study. You can call it a color study I've done. I like to pull it into color moves and then use the palette functions in color moves and create a completely new display and art form, for lack of a better term. And you'll see I'm doing that here. I had a great time. I loved the tool. Anyway, if you follow my blog, you'll see that I do that a lot, and I just love it. So I wrote this book, and it contains a lot of the concepts I covered, specifically the ones I cover in my first lecture on color theory. I also go through a number of color tools. I cover something like Copazzo, which is from the Color Lovers group of people. That's another good tool. I do cover ColorBrewer. I cover Adobe Color and how to use it in the book. I cover some Coblis, definitely, in the book. Because it was published in 2016, so most of the content was written in 2015. Some of the updated functions, like Adobe Color's capability to support accessibility tools, is not in the book. But then what you can do is, I'm writing for Nightingale, and I started writing due to all this COVID situation that we're in. I started writing in March and April. I started writing, and I produced about 10, 11 articles. I think I'm on the 11th at the recording of this video, and we'll see whether more come out. Let's put it that way. For some of you who know me, I love to ballroom dance, and I can't ballroom dance in COVID, so I'm writing some articles in Nightingale. And I'm having a great time doing it. It's an incredible group of people, the Data Visualization Society. I've got some great editors that have helped push me and learn more about color than I ever thought I was ever going to learn. I cannot say enough good experiences about it. So you can catch my latest writings there, or you can buy my book, which I love, if you would, Applying Color Theory to Digital Media and Visualization. If you want to hold in your hand some of the concepts, the written word concepts of what I've got, you can also get a digital version of it too. That's become very popular, by the way. The digital version is selling more than the actual physical book at this present time. So now I want to review some of the mobile color apps I've covered in this tutorial. I covered Adobe Capture. It's a free mobile app. It works on Android as well as iPhones. So it works across the gamut. It's not device specific, except it's mobile device specific. And I covered Pantone Connect. Again, this is a free web and mobile app with $4.99 providing complete access. But Pantone, right now, due to COVID, has left a lot of this free. And they're still in discussions about what they're going to charge. Right now, everything you want to do with it, Pantone Connect, is free. So you'll see, they're thinking about keeping some of the basic functions free and not charging for it. But it's up and down. They debate as to what they're finally going to do. It's really up in the air. So there's some online tools. Again, I mentioned to you Adobe Color. This is like, I call it the grandmother of color tools. It is, and that is continues to evolve. It's an amazingly powerful web tool. Palladium's Color Scheme Designer. This is one I'm particularly fond of. I did a very detailed Nightingale article on how to use it. I really like that particular tool, and I did some examples earlier. The Tetrad example I did was done in Palladium Color Scheme Designer. Again, remember, it used the red, yellow, blue color model rather than the red, green, and blue color model. But you took my course, and you know the difference between the two. ColorBrewer, that is our classic for visualization. So if you're going to do visualization, it's a good idea to know how to use ColorBrewer for your sequential, diverging, and your qualitative color maps that you're going to build. And it ties in well with Tamara Munchner's book that's now become a classic in visualization. Viz Palette, I've showed you how to use it. I really, really like this tool. It's publicly available, and I like the fact that they also cover color deficiency in the tool, but it gives you various quick tool to give you visualization options that you might want to use. So Susie Lou puts it out there for you. All right, so now I want to remind you again about color blindness simulators. I want to tell you a little story. I used the supernova example. I want to tell you another little story. My first visualization, really big-time visualization work I ever did, was at the United States Environmental Protection Agency, and I'm visualizing some data from Lake Erie. And the guy wanted a graph, and I put a green graph paper background. I was trained as an engineer, and I thought that looked like great engineering paper, and I put a pink line across there. He called me on the phone and said, I can't see that. I cannot see the line. His son tells me on the phone, my father is colorblind. That's the first time I learned about color blindness. And then I had to put in a blue line, which the researcher saw, rather than a green line. So I learned it in the field, and so I try to use color blindness simulators until I conveniently forget, go and work with an astrophysicist, create an award-winning visualization that does not pass color deficiency test, and I find out later, but hey, it happens. Anyway, I would suggest you use color blindness simulator, but be grateful that ColorBrewer has color deficiency addressed in it. It's the little I on their icon. Be happy that you can get it from there. Viz Palette. Now, they don't cover Tritanopia because that's a very small percentage of the population. So it's possible to get some Viz Palettes in there, Viz Palette examples that might not pass Tritanopia. Kobelisk, and you can check it with that if you want to. Palladium's Color Scheme Designer. It's amazing, you know, Palladium and Adobe Color have been out for a very long time, and it's amazing the power that Palladium has with regards to the ability that they address color deficiency really very early. And now Adobe Color, with its new capabilities in June or July of 2020, addresses color deficiency in its color swatches now, its color themes. Okay, so now I'm going to cover some other books on color that you might like. So this is a new, spanking new, A Natural History of Color, the Science Behind What We See and How We See It. It is a terrific book. It just came out in 2020. It's recently been reviewed in the last, I'm talking about 2 or 3 months. And you might like it. If you really love color science, I think you might really like this history. I think it's very fascinating. Okay, Maureen Stone wrote a really wonderful book on a field guide to digital color. This came out before mine, and it's a terrific book. I think you'll find it to be really helpful to you if you like it. The Interaction of Color by Joseph Albers. You can now go ahead and get the app. The app is set up so that you can actually get digital sections of the book in it when you pay for the app. But if you want to actually have the book that you hold in your hand, some of us still like to have that. You can get that from Yale University Press. They give you all the options. They show you how to get the app, how to get the high-quality coffee table book, how to get the more portable book that he's got, less expensive, more portable book. The digital print, preparing images in Lightroom on Photoshop. For some of you who are really into printing, Jeff Schwee is an amazing pioneer in this area. He is a true Photoshop Lightroom guru. This is an excellent book. I would recommend that you consider that one. And then Cynthia Brewer, Esri publishes her work, Designing Better Maps, a Guide to GIS Users. This is an incredible book for trying to understand further how she does design with regards to, she's doing cartography, she's an award-winning cartographer, but you might be interested in, since we're a visualization community, it's closer to that. And then I thought this fun book, for some of you who might like animation, The Color of Pixar. This shows you the color combinations that Pixar has used with regards to its movies. By the way, Pixar and those kind of color combinations are even setting standards. Pantone actually every year comes up with a color of the year, and they actually look to see what's going on in digital cinema, to see what colors are going on there because of the various color maps that have gone on in digital cinema. See if that affects the actual color of the year. So there's a couple books I gave you, just if you like it. You can get some of these online. And I would go for the natural history book because it's a really cool book. All right, so I had a great time talking with you. I think this lecture is even going to be under an hour. I designed it to be an hour, but I probably talked a little less, but that's okay. We can chill out together. My most recent work was inspired by a color scientist named Dorothy Nickerson. Now, I've left it for you guys to Google her, but I'll give you, since I got a little time here, I'll give you a feeling about her. Dorothy Nickerson worked with Munsell, and she was involved with the Munsell company that existed just after Munsell died. She continued to work with them for a while. She also went on, then she went with the Department of Agriculture, and you'll still see that Munsell is still used as a color standard in soil samples. And that's because of the work that Dorothy Nickerson did. Nickerson also developed some of the algorithms that made CIE Lab. She is one of the co-authors on some amazing color algorithms, and she went on to help pioneer CIE Lab as to what it is even still today. So she was she was also a very good educator. She had an amazing career with the government and influenced a lot of color science. So you can Google her. Her Google bio doesn't give the kind of depth that she actually is. You need to talk with people who are in color science, but you'll find out she was an amazing pioneer, and she has inspired my work a great deal. I'm always indebted to a lot of colleagues in the visualization and digital media community have helped me so many years. I can name so many of them. If you want to go back and look with the various people I've worked with, just kind of Google and study my history, you can find them. But it goes all the way back to some of the pioneers who won amazing awards in computer graphics, to leaders in visualization. And I thank all of you. But I also want to say that I have been amazingly reborn again by the Nightingale Data Visualization Society group. They have really appreciated my work and showed me and pushed me to go in new directions I would not have gone in had it not been for COVID forcing me to give up my ballroom dancing and focus on writing for Nightingale. Can you believe that? But I also want to give a shout out to them. I didn't put it in here formally, but I really do appreciate the work that they've encouraged me to do over the last 6 months. Okay, and I'm always indebted to my family members. I come from a family that has a thing, I think Bernice Rogowitz told me once, it has a thing called color memory. For years, we could accurately, we didn't need Pantone, we could accurately say, do you remember that suit you bought, or that dress, or do you remember the wall that we painted, or something like that? And we could remember the colors between us. And it was not until when I went out into the world as I grew up as a child that I learned that not everybody else had that color memory. So I'm indebted to my family very much, because they look at my color writings and they told me if I goofed it up too, since they have very good color memory. Okay, thank you all. And I have much appreciation and gratitude. I'm also probably going to need to thank the people that helped me put these videos together, the technical team that are associated with making IEEE VIS 2020 happen. I'm indebted to all of you, because you're going to make my stuff a reality, and I thank you very, very much. Okay, I had a great time. I'm going to close out now. I don't know what we're going to do, because I know that I am under the 1 hour limit, but maybe you guys can chill out, or we can go into the question and answer early, or whatever happens. Thank you very much for listening to me. I love color very much, and I love talking about it. Okie doke. Any questions? I'm delighted to answer them. Okay, there's a question of Color Oracle. I don't have a lot of experience with Color Oracle myself. I'm just learning how to use it. I just try to keep up with all the tools as best as I can. Let's see, Klaus asked me a question about Pantone app can also extract colors from images. Yes, it can. The difference is that when you work with Pantone Connect, you're only going to get colors that are in the Pantone library. Whereas when you work with Adobe Capture, what you will do is you'll get the broad range of colors that are basically have a web, what do I want to say, a hex value on the web. So you're going to get a broader range with Adobe Capture than you will with Pantone Connect. But you want Pantone Connect if you're going to do things like printing or work with textiles, do a t-shirt design, because you want to know how those colors are, color inks are going to appear and be printed. I hope that answers your question, Klaus. The other thing to know about Pantone colors is most of them are fully saturated. You're not going to get a lot of the lighter tones, or you're actually not going to probably get tones, tints. You're going to get straight ahead hues with Pantone Connect. Actually, that's something I've recently been talking with Pantone about. So that's going to be the big difference. So Pantone Connect gives you the extraction from an image is only going to give you Pantone colors, Adobe Capture will give you a broader range of colors. So remember, what you're going to do is you want to use Pantone Connect when you're going to transfer into a medium outside your digital world. And also when you want to talk with various people in the color production industry, a lot of them talk Pantone, and a lot of us in visualization don't talk Pantone. Now there's going to be, you might want to look at the Nightingale article that I wrote that goes from digital to printing, because I showed you how Adobe Color can show you various Pantone colors, but there can be a lot lost in converting, which most of us probably know that there is a loss when you go from digital to print. So you might want to see what that's about. So sometimes you might want to directly design in Pantone. That's why you might use Pantone Connect. Let me tell you now, Andre Matisse was around way before there was Pantone Connect, but Matisse later in his life, he produced a book called Jazz, and it had a lot of cutouts in it. And Matisse intentionally worked in construction paper because he was very aware of the fact that when that book was produced into a book, he would have the actual colors that were associated with what could be printed at the time. So many artists also know that if they're going to print or stencil or something like that, they're going to use a different color palette than they might if they were just going to straight ahead paint. Naomi Ramos, yes, you can still use VIS check to check for color deficiencies. I do that all the time. The only parameter that VIS check did not include was Tritanopia, and that is a much smaller part of the population that have Tritanopia. I'm going to put down, so VIS check does not have Tritanopia. So that would be the only differences in the tool, but that is a small part of the population that have that deficiency. But I have used several times, I have just only used VIS check and it's come out fine. Okay, I got a question. So with regards to color blindness, the goal is to make sure the colors are distinguishable. Okay, all right, let me see if I can try to explain this. What happens is when you have a color deficiency, there's a range of colors that you cannot distinguish. That's true, but you want to use a color blindness simulator because it's not a case that you don't want to use red or you don't want to use green. What you want to see is there's a range, the individual with the deficiency can't tell the difference between the two colors, but there's a range of colors that they can work with. So by using a simulator, color blindness simulator, you can see what range that you are in. Like there might be a combination, a color palette that has some pinks and some greens that might work well for someone with color deficiency. So it's not an always positive thing. Don't use red or don't use green. There is kind of a range of colors. That's why I was trying to indicate earlier in my first lecture, I was trying to indicate that we're not like a cell phone and that you can say that our red and the red and green light is not working with regards to how a projection system. The color deficiency is across a range of colors and there's variances. I hope that answers the situation, but I always find that I can't just, I've done this a lot and I can't just guess what's not going to work and what's going to work. I really like to use a color blindness simulator a lot. Eight plus colors, that's going to be rough. In general, I've actually just been writing, I have a new article that I'm going to be putting out for Nightingale in probably in a couple of months. When you get up to 8+ colors, normal vision people can't distinguish that many colors. It's been shown that that's the case. There's an article in a biologist wrote on flying colors. And he was talking about how when you get between, the way it goes is you can create a safe a colorblind safe palette at about 4 colors consistently. When you get into 5 colors, it gets 5 distinct colors. It gets tricky. You can do where you can do a sequential color map. You can do a diverging color map where what you're doing is you're doing a range of colors from a white to from the light tint tones to the grayscale. I mean that for the color. So let me see. I'm thinking a little too quick here. Let me say. I covered earlier. What you have is if you have a sequential color scheme, what you have is you're going from white, then you're going to add a little bit of white to the saturated color. Let's call it blue. So you're going to go to a tint, then you're going to go to a shade where you add a little bit of gray, tone, excuse me. You're going to go to a tone where you add a little bit of gray. Then you're going to go to a shade where you add a little bit of black to the hue. And then you're going to go to the complete hue. Colorblind people can see that. This was sort of shown by actually Ansel Adams himself, created a system, I'm going to call this, he created the zone system, if you want to ever check this out, where he really showed what people could look at, this was Ansel Adams, how well people could see gradations in black and white. And the same is true for a single hue, which is what a sequential color map often is a single hue. When you get into analogous colors, which is 4 or 5 colors next to each other in the color wheel, someone with a color deficiency cannot easily distinguish between them, and people with normal color vision cannot distinguish between them. If you get up to 8 gradations of color, people can't distinguish between the colors. So it's recommended that you stay 5 to 8 is even tricky. 5 to 8 is tricky, but so it's not easy to do. That's what I do, and what I'm going to cover in this new article. I want to say 5 to 8 is tricky. Is I'm going to show that what you do is you double code. So if you have, suppose you have 8 different colors that you want to cover. What you might want to do is add, say that the data set pertains to countries. You might want to put inside each of your colors the name of the country. You want to double encode it. Or you might want to come up with 1, 2, 3, 4 on a map. So double encode it. So you want to add information into the visualization that is not just color, but also provides additional information to the viewer. So if they can't see and differentiate between the colors, they can also refer to the items that you've depicted in a different way. Five to 8 colors, color palettes, I'm going to say, are a challenge for deficiency. Okay, interested to hear a little bit about the machine learning for colorization. Do you think the color of the pumpkins in the middle of the tower could have been based on a tomato? That's cute, tomato images. No, in terms of that particular example that I showed in this class, I know they were all pumpkins because I took that image, and I don't think they were based on a tomato. In terms of machine learning, I think that what's going on with regards to that particular photo colorizer is they're not smart enough to they're not trying to discover, they're not looking at it and saying, okay, that's a pumpkin and I'm going to color it orange. They're looking at more something to do with the pixels and then colorizing it for that. So it's not that smart to colorize. It's not guessing the object and then colorizing from a library. That's Elizabeth's question. It's colorizing straight from the actual texture of the actual elements in the photograph, trying to guess it. I hope that helps, Elizabeth. But that particular colorization, it was really based on taking black and white photographs and then trying to colorize those photographs. It did not, the guys did not have a library of where it could sense what the particular photograph was about and then colorize accordingly. But it would be good if they had something like that. That would be really great. Yes, Elizabeth, you're right. Lower level image properties, not like Google Object ID. Absolutely. But I think people are probably working on it right now. I'm going to make a guess that people are probably, machine learning is advancing so well that it's going to be happening soon. The only trick I found with trying to use some of these machine learning algorithms is sometimes it's, I tried this way, sometimes it's too smart. In other words, it will start to, in the world, there's a lot of gradation. If it looks at it and says, I'm looking out my window right now as I'm talking to you guys, and I'm seeing some autumn leaves, and it might try to make a decision about particular colors. And actually nature can create a gradation of colors better than what machine learning can. And then our human eye can see that gradation. That's the problem with using a pure machine learning algorithm to colorize, is it doesn't get the various tones and tints of a color that nature can do and that artists have learned how to do. But it'll get better. Yes, it did. You're correct. It did impose gradations on my solid black and white color experiments. Yes, it did. But I did a bunch of experiments where I put in different grayscale photos where I changed the scales to not be as clean black and white to be more grayscale, and it came up with different color combinations, which is fine. I didn't use that example, but I will for another tutorial. Thanks, Elizabeth. That's 2017 work, so that's getting to be older work. There's been a lot of advances. That's why I'm saying there's a lot of advances really going on right now in machine learning. Any other questions? I see. Okay, professional photographers say they couldn't use Kodak film due to bad color. However, color took into account perception. Elizabeth, that's an excellent comment. I understand about okay, Kodak and what they discovered in their research labs and film is really amazing. And so much of that work, they didn't really publish it. Like you're noting, what they did was they sort of readapted how they processed film according to what they discovered, but they didn't necessarily put that out into the world as like research papers and elements like that. If you're interested in those types of things, the best group of people to just kind of look at their work is the Rochester Institute of Technology. They have a whole group of people on color out of RIT that can find some various archives and things that were going on in terms of for Monsell, for Kodak, for those types of things that are uncharted, undocumented. But yes, indeed, there's a lot of, shall we say, tricks that people know about color or do with color, and they don't necessarily record that. I went, in my example I did earlier in the talk, I showed a Monet painting. And at one time, I went and put a bunch of color tools on various Monet paintings. I was amazed to know how much he had learned over the years of how to adjust his color palette and move things around. And a photographer learns that. If you read about, Ansel Adams only worked in black and white, but after he died, they put out a book on his color photographs. And he was very frustrated by color because he could not control it as he could with black and white. He couldn't develop the techniques to match up against it. And there are other people who have developed and mastered color. I'll give you one of his students, just as some of you want to see it. Don Worth, for example, a color photographer, did master color and did learn how to see a color shot. Similar to what Elizabeth is talking about from Kodak history. So there's a lot of tricks that people learn. Not sure, okay, Klaus, not sure if this is the same one, but playing with color harmonies in Adobe Color. I noticed with the Analogous, the generic colors have slightly different saturated brightness values. Stay constant. Okay, Adobe Color is willing to I want to see it move between various color gradients. I mean, what you're saying, Klaus, is very true. It just has to do with that algorithm. It has to do with the algorithms that Adobe Color put into automatically selecting its analogous colors, where it will all of a sudden flip out. It'll come up with a tone, it'll come up with a tint, and it'll come up with a saturated color all next to each other. And that's a good observation, Klaus. I've had that happen to me as well, where I will notice that Adobe has not given me equivalent colors all across the board, and it's 5 that it puts out there. It's just in the algorithm and the way they wrote the algorithm. I really can't, I don't work with Adobe directly, so I don't know the inside of it. But you are correct in that they do not use a pure color model with regards to the colors they generate. That's a good observation, Klaus. The same things, by the way, is also true with Adobe Capture, which is their mobile app. By the way, HSB and HSV are very similar. HSB was around before HSV. Goes back into HSB goes back into the late 1800s. HSB, 1970s. I talked about Ogden Rude's book covered HSB. My dream would be if my book could have the power that Ogden Rude's book had to sort of explain it to you. Imagine that the Impressionist painters were reading Ogden Rude's book and experimenting with it, the color concepts he talked about as they started painting on canvas. That is to have an incredible impact. Interestingly, Ogden Rude didn't necessarily like having had that impact. He didn't necessarily like Impressionistic painting, but his book had that kind of impact because he was able to explain color theory so well. But I got Rude's book because I'm a color geek and I wanted to read it. Color geeks like to go to libraries and read really old books and just sit there. Sometimes you have to sit in the library for quite a while because they don't want you to take the book out because it's a rare book. And I sat there and I read and I could not believe in the appendices. He had covered all these concepts that I thought were done much later, but he had them in his book. So he really put cutting edge concepts into his book. I don't know how long the YouTube tutorial video will be available. Someone from the Biz Tech team needs to answer. I can't answer that. Oh, wait a minute. Wait. I can answer that. It is in the proceedings. So that should make it available for however long those proceedings are available. I think so. I think that was $10. I think that was a $10 registration fee. Somebody correct me. Wasn't it $10 and you can access the digital proceedings? I think completely free, you didn't get access to the proceedings, and then $10 you got access to it. It's under, it may not be listed directly, but it's under like other content or something. There's some videos for the tutorials. Elizabeth, that's kind to say so much to absorb. That's kind. Thank you very much. We're almost to the end, am I right? We've got 6 minutes left. They're telling me we got 6 minutes left. So 6 minutes for questions, everybody. The other thing you can do is follow me through Medium and medium.com and Nightingale, because I'm going to continue writing on color. So I've got new thoughts and new ideas that I'm thinking about. Like I've really got a new writing that I'm I haven't completely finished yet. It's on categorical colors, because I've thought out about the fact that question about 5 colors, 8 colors, I've thought out about that. So I'm going to try to put a writing out on it. So I think about color all the time, and it's taken me years to get to the point where I could actually write about color well enough. For a long time, I did visualization, and I did colorization, but I couldn't really write about it. I could feel it, but I couldn't really write about it. So I'm having a great time because Nightingale has been so good to me and providing me with such an excellent editor that I'm able to write that stuff out now. I kind of feel like I understand Ansel Adams later in his life. I'm nowhere near where Ansel is as an artist, and nowhere near things that I want to comment on. But Ansel Adams later in his life began to write a lot of books. And I can relate to how you finally get there, and you just want to keep wanting, you want to share it so much. Oh, I should tell you, there's another conference. You might, if you're into color, there's another conference that's going to come in 2021. It's called Color Impact. You might want to follow this. This is something if you want to just sort of see what comes out of it. It's going to bring a whole bunch of people who do color in all kinds of different industries and disciplines together. And it's going to come, it's probably, they want to hold it at Yale. It's going to be held at Yale University, because that's where Albers did a lot of his work, but it's going to be there. So if you're into that, that's going to be coming in 2021. And then I'm going to say to you, watch for Pantone Color of the Year announcement. It's coming in November 2020. I meant to say November. So now that you guys are semi-color geeks, you might want to watch for that announcement, what they choose to be the color of the year. Thank you all. I really enjoyed the questions. It was really, really a fun session to do. I love color very much, and it's always nice to come back to the first conference that gave me my chance to publish this work. I published my original work at IEEE VIS, so it's always nice to come back. And I thank very much the IEEE VIS community for letting me come and give this tutorial. I had a great time. And what do we got left? 1 minute? 2 minutes. He says I got 2 minutes left. Check out the afternoon tutorial. It should be really, really cool. One minute and counting. Bye.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
We propose X-matrix, a novel method for random forest interpretability. From a random forest model, a logic rule is extracted from each decision path on every decision tree. Once the complete set of logic rules is obtained, visual representations can be built for global and local explanations. X-matrix, making random forests interpretable.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
How do we represent remote users in synchronized visualizations while supporting divergent exploration? We present cursors, the basic unit of user representation in a collaborative visualization. They can vary significantly in appearance, as you can see. Cursors enable collaborative interaction techniques, such as peeking, tracking, and forking. To learn more, please read our paper representing real-time multi-user collaboration and visualization.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the CN model is not easy to understand. We introduced the explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the explainer, users can progressively explore the CN model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
CMED is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing.